Hello to everyone who's watching this video. First of all, I would like to thank the organizers for giving me the opportunity to present my work in this nice idea of a workshop. And what I'm gonna report today is some recent joint work with Richard Oberlin, Luz Roncal, and Andreas, Seeger and Betsy Stovall on variation bounds for spherical averages. So before jumping into the topic, I'm gonna start revising very quickly the setting of the spherical maximal function to better understand the framework for our results later. So let's start by setting some notation. AT is gonna denote the classical spherical averages. You get a point X and you just draw a sphere centered at the point of radius T and just take the average of the function over that sphere. And of course here, the measure is normalized in R1. And given this family of averages for all t, we can consider the associated spherical maximal function defined through the supremum over all these possible dilated averages. And it's a very classical result of Stein and Bourgain. This object was introduced by Stein, that the spherical maximal function is bounded for all p, provided p is greater than d over d minus 1. So here, in contrast to the usual hard deletable maximal function, which can go bounded for all p is really greater than 1, we have this d over d minus 1, where the d minus 1 here appears because it's the dimension of the sphere on Rd. So for d greater or equal than 3, this was proved by Stein. The case d equal to 2 is a little bit more difficult. And was proven by Bourgain, and then an alternative proof was given by Seeger and Sock based on local smoothing estimates. I'm mentioning this because this will play an important role in the basic strategy that we follow. Also, some LPLQ bounds have been studied for spherical maximal functions. In this case, in order to have LP2LQ bounds for P different than Q, P still is more than Q, we need to restrict to supremums to a local supremum. We need to restrict to supremums for times between 1 and 2. And this was studied by Slack and Sock, who obtained the whole picture, these diagrams, except for an endpoint in dimension 2, the endpoint bound in Q4, which was obtained by Sanjukli a few years later. So far, these pictures, let's not try to understand these pictures. It will become appear in a second why these pictures have this shape. The only thing I want to remark at this stage is that this is, of course, the 1 over P, 1 over Q picture. Here, there are two lines that give rise to this quadrangle here. So this point Q3 is lying into the Q equal P prime, right? So it's the anti-diagonal. And here, this is another line, which will reflect on what this is later. And for dimension 2, these points Q3 and Q2, they coincide and they equal to the point 1/2, 1/2. So this is why it gets raised to a triangle. So, let's get started with what is the basic strategy that one follows to study spherical maximal functions, or one of the possibilities at least. And even when the supremum is taken over all times, for the classical case of Q equals to P, we basically restrict always ourselves to study what happens for this T between 1 and 2, the single scale one that appear for the LPLQ bounds. And one can always put things together for all possible time scales by Little-Pelli theory. So from now on, we only consider these supremums. The second reduction is that we'll look at a single frequency piece. If we don't aim for endpoint bounds, or we only aim for endpoint bounds in a particular kind of way, we only look at a single frequency piece and want to establish a decaying estimate, like a favorable estimate in J for the localized frequency piece. Here, Fj has frequencies at size 2 to the J. So we aim to just study the operator acting on these functions and obtain a favorable estimate in order to be able to sum over all possible J's. So we want to determine for what's P and Q, there is a epsilon PQ that is strictly positive. Then the third step is to apply a Sobolev embedding and to replace the supremum by an LQ norm. So that then we are studying space-time bounds here, but for the same Lebesgue exponent Q. So of course, this induces a loss. This is replacing the L infinity by the LQ, and the loss is 2 to the J over Q, because we are losing 1 over Q derivatives. So the fourth step is, well, we have translated our problem into study LQ bounds for the same P and Q. LQ bounds for space and time instead of taking here a supremum bound. Well, this allows us to now integrate in X first and later in T. Rather than in here, we had to do things in T first and later take LQ norm in X. So one can start by looking at what happens for a fixed T, and then just see if I can integrate trivially in T, because this is a compact interval, and then just get away with the information for fixed T. So this is what I call here, what people call fixed time estimates. And there are a bunch of available and sharp fixed time estimates in the literature. For instance, they can just be obtained by studying the average is just a convolution, right, with the measure. So one can look at what does the multiplier look in Fourier side. And it is very well known by stationary phase methods that the spherical measure has Fourier decay of the dimension divided by 2, dimension of the sphere divided by 2. So then Plancharel already gives an L2 estimate with this, like an L2 Sobolev estimate with this Sobolev index. And because it's bounded in L infinity and in L1, one can interpolate. In particular, for Q greater than 2, one would obtain minus D minus 1 divided by Q, which let me rewrite that as first a gain of 1 over Q derivatives here, and then the remaining part. The reason why I'm writing it this way is because now the loss from Sobolev embedding cancels with this one, and then this is the proper epsilon PQ, epsilon QQ in this case that we have. So you know that for D greater than 3, this is summable. For D greater than 2 is not. So at least for D greater than greater or equal than 3, we are done, and this is how one proves one possibility to prove Stein's theorem. So for D equal to 2 is not enough. The reason is because we are losing always the same number of derivatives here, independent of dimension, but the Fourier decay gets better with dimension. And we'll see how to solve this in a second. Let me say that there are trivial of diagonal estimates by looking at this LQ estimate and interpolating it with an L1 and L infinity. This just comes from the fact that when we are taking this Fourier localization at frequencies 2 to the J, then we are turning our spherical average into like an annulus average. And then when we look at L1 to L infinity, we are picking up the width. So that interpolating that gives us a bunch of estimates. This has a loss, so there will be a middle point in which things compensate, and this epsilon is as small as we can make it small. Okay, so this is the basic strategy. Of course, for D equals to 2, this is not enough, but here we are only considering fixed time estimates, right? So the key idea is to, when we are integrating in time, to do something better. And the reason why we can do something better is because instead of just looking at the Fourier decay, one can look at the precise form of the Fourier transform of the measure, and this carries some oscillation. So this connects the spherical averages with the wave equation, and with Fourier extension operators for the cone. And using that, one can obtain better estimates. One can obtain a sigma gain with respect to the fixed time estimates for these operators. So this was first observed by Sock, and there's a conjecture called the localized smoothing conjecture for the wave equation, which tells us that the gain should be of 1 over q when p is equal to q, and has been recently solved in dimension 2, and in dimension 3 we have it for not. So here I guess I forgot to put q greater than 2d over d minus 1, and here we have a partial range given by the Burgan-Demeter inequalities in which this holds. For the maximal, there is an LPLQ version which would follow by interpolating this with this L1 and infinity bound from before. So for the maximal problem, we don't need the full strength of this. So in the case p equal to q, we were only away from an epsilon, right? And then for the case p equal to p is 3 smaller than q, instead, some sharp regularity estimates are needed. So we need to go up to the full regularity gain. But in this case, this turned out to be easier because really a primary instance of these local smoothing estimates is the classical Stein-Thomas Strickhardt estimates for the cone, because by Plancher's theorem, this can be recasted as a local smoothing estimate for exponents p and q, where p is 2 and q is 2d plus 1, d minus 1. This is the only instance in which Fourier restriction and local smoothing they're equivalent, and it's thanks to the fact that p is equal to 2. So note that this is much earlier work than Sox, but it had never been thought about in these terms before. So with all this, then what happens is that when one looks to the case dimension greater than 3, we already realize that it was good enough in this line. Then we can also get it in the anti-diagonal with that trick of the L1 and infinity bound. The Strickhardt estimate is a point here which has decay and is the best possible one, is sharp. So then one interpolates that to the L1 infinity, and then one in here gets the other point Q4. And the Strickhardt estimate lies in the point for the local smoothing point conjecture with the L1 and infinity. In dimension 2, what happens is that we needed actually these local smoothing estimates already for the line p equal to q with just a little epsilon. And when p is different than q, what happens in that case is that the Strickhardt estimate lies outside our it gives us a positive exponent, so it doesn't carry a gain. So the work of Slack and Sock was to prove points in here which have a sharp gain, so that you can obtain the Q4. So of course now this follows as well from the Wood-Wang-Zhang result, but the endpoint does not, and the endpoint still needs the work of Lee, which relies on Tao's bilinear endpoint restriction theorem. Okay, so just giving this quick review, our goal is to really study this variation for spherical averages. So in here, what I'm doing is I'm replacing the L infinity norm by the larger BR norm, where I'm taking the usual definition for variation, which is we take the supremum over all possible partitions when we are given a sequence, depending on a parameter. So we take supremum over all possible partitions of the little error norm of the differences between two consecutive values in the sequence. So we can then define the global variation operator and the local variation operator, where global is we take times all times between 0 and 1, local is 1 and 2. And for the global one can study LP to LP bounds, and for the local one, LP to LQ bounds. So the case that had been considered before, it was the global case. And here there is a result of Jones, Seeger and Wright, where they obtain pretty much the full picture. And everything here is sharp, except for, and how the estimates evolve is that we are restricting the range of boundedness with the value of R. As R gets smaller, instead of having all P's greater than D over D minus 1, we restrict the range of P's from above. So P doesn't get to be bounded at infinity. as R starts to decrease. What happens here as well is that note that when we have a maximal function, the L infinity to L infinity bound is always trivial. So we always have strong bounds of L infinity type. However, we lose that bound when we try to apply the same kind of a strategy as before. We seem to lose that bound at the point in which we stop the boundedness, which in this case amounts to this P equal to RD. So in that case, this was left open, what happens in this point, and a first result that we obtain is that the operator is of restrictive weak type at that endpoint. So this is we don't know if it can be better or not. We don't know if this is sharp, but at least we have a positive answer of results in that direction before no results were known. So, but this is not the main goal I want to discuss. The main goal is to look at the LPLQ bounds for this variation, for the local variation of spherical averages. So in that case, remember, this is the picture that we had for this quadrant. The big quadrangle is what we have for bounds for the spherical maximal function. Now the variation is a larger operator. So in the same way, therefore LPLP bounds, the bounds shrink. When we decrease the R here, the same phenomenon happens. And then how it goes is that an horizontal line starts to appear that restricts our bounds. So we have this point PR, this horizontal line that starts to travel, and it starts to travel until we hit the point Q4. Once we hit the point Q4, then we have another point PR that travels along that segment, and then the bounds here, they have this Q1 continues to go horizontally, but the PR goes at a higher speed along this segment. Here there's a little bit of a tilt. And then once the PR hits Q3, then the point Q3 starts to travel along the anti-diagonal. And then we are also shifting our bounds to the left. And we start to incorporate a vertical line. So the results that we obtain are all, they are all sharp, in the sense that bounds fail if we are outside the closure of the regions that we're considering. We obtain sharp results in dimension greater than 3, greater or equal than 3, except for a range of R's. Here, R, we always take it to be greater or equal than 1, because it's the Banach space range for the variation. For D equal to 3, we don't get quite the full picture. I'll explain later why. For D equal to 2, we get it. I didn't draw the pictures here, but we get it thanks to the good Wang-Zhang, actually. But what is interesting here is that we are also obtaining strong bounds here at this boundary line. So this is related to what I was just saying before, that that for maximal functions, one has the L infinity bound for free, right? For variation bounds, this is no longer the case. For the global guy is where we obtain these restrictive with type results. Here, however, we are able to obtain strong bounds at this boundary edge. And this will be one of the results I want to focus later. So let's just describe a little bit the bounds that hold in the interior before we jump into this boundary endpoint. So in here, the basic strategy again is the one I described earlier for the spherical maximal function, with like a couple of necessary twists in order to obtain the optimal bounds. So the first one is that the embedding that we use, instead of being the usual Sobolev embedding, we use like a natural embedding for the variation spaces in terms of the PS of spaces. And so now, instead of losing, we replaced before we had a supremum, and we were replacing it by an LQ norm. Now we have a BR norm, and we can replace it by an LR norm, losing 1 over R derivatives, right? So then one wants to establish now, instead of LP here LP in the right to LQ in both space and time, what we want to establish is we take LR in time first, and then LQ in space. Okay, so that's the difference, that we are incorporating a third parameter R into our analysis. And from now on, I'm going to use this notation in which I use this calligraphical AJ as being my averaging operator with the cutoff incorporated in time, so that I can write for sure this LQ brackets of LR as meaning what is on the right hand side in the inequality above as here the LQ are the with LR in 1, 2 in the time interval. Okay, so that's the first twist. The second twist is that remember that we had that annulus estimate. So that annulus estimate, if we are integrating in time first, and then we take L infinity norm in space, here integrating in time cancels this loss, the 2 to the j loss that we had earlier. So here we had like a better L1 to an L infinity of L1 estimate with no loss, which can be used to interpolate and lower the value of R everywhere. And the third key ingredient is that these local smoothing estimates, now we will naturally look, instead of LP to LQ, to LP of LQ of LR type of local smoothing estimates. And the classical Stein-Thomas estimate that I said can be recasted as a local smoothing estimate admits like a square function version. This is also like a classical result in which this LR can be here at 2. And then we had this decay minus j d over q. So these are the 3 possible main ingredients. What else do we have to take into account is that, well, the operator is essentially local. So whenever we have a bound, we can always do a localization and a Helder argument and increase the exponent, the Lebesgue exponent P on the right by keeping the Q and the R fixed. Okay, so this is just because the operator is at unit scale, really. We are only taking supremums between T1 and 2. So if we localize the input function on cubes of size O of 1, the output doesn't change, doesn't delocalize the support, right? So once we have a point here, we can go to the left, kind of. So we can always interpolate with trivial heres at the L1, L infinity of L1, and the triple L infinity, and then we can go to the left by doing this localization argument. So just as a sum up, then one interpolates the many estimates that one obtains at the different corners of this picture. Is like a numerology challenge to do all these interpolations correctly, but this is how one gets all the bounds in the interior. Okay, and these bounds are all sharp except what happens in this blue triangle here. So in this blue triangle here, as I said, for the equals to 3, we don't quite obtain the results that we want. Okay, and what is the reason? So the reason is a little bit similar to why dimension 2 was more difficult for the spherical maximal function. So now introducing this variation problem is not only that dimension 2 is bad, also dimension 3 continues to be bad. However, for dimension 2, because we had the local smoothing conjecture solved, we can get away with it. But for dimension 3, we have a partial range. Okay, but the reason why we have this bad for lower dimensions and good for higher dimensions is that it's fairly artificial, in the sense that the problem should be appearing in all dimensions. And the problem does indeed appear if one, instead of restricting to this Banach space range so that the variation not makes sense and R is greater than 1, if one allows the R to be more than 1, which there is an alternative definition for variation in that case, then the analysis that we are giving gives us bounds for R is more than 1 but greater than this threshold, where this number here is the Stein-Thomas exponent divided by D. And this is because we pivot our analysis around the time to mass. But what one can conjecture is that one should be able to go to this exponent here, yellow on the left. And what would be this exponent? This would be the restriction exponent divided by D. So the restriction exponent or the local smoothing exponent. So one can conjecture that there are results there. And you can see that for when D is dimension 2, this matches with this red here are greater than 2. So what is happening here is that this conjecture that we are making, it seems to be weaker, of course, than local smoothing or Wagner-Riess, but a little bit stronger than KK. So it seems to be like a version of Wagner-Riess where, or like a square function for Wagner-Riess, where we have the LR norm doesn't need to be equal to 2. So it can take smaller values of R. However, we really, there are no techniques when it doesn't seem to be a benefit so far, how to exploit R being smaller than 1. This is a nice picture that Richard Oberlin made to understand better what are our results in a 3D picture. And this is what I said, like the blue part here is R equal to 1. So is the usual Banach space range. So for dimensions greater or equal than 4, we obtain the sharp results there of this shape. Then the results can be extended to this purple part when R goes smaller than 1 and the exponent that we just left. And then we have then this yellow part, which is open. And this is open in all dimensions, right? Including 3. But for this lies precisely in the Banach range. And this is why we could observe a sharp region in dimension 3, but not in higher dimensions due to this Banach constraint of R greater than 1. So this concludes the case of the bounds in the interior, but let's look at the bounds on the boundary edges very quickly. And with that, I finish the talk. So as I said, the most difficult part in our theorem was to establish this boundary edge because it cannot be just obtained via single scale analysis. All the other endpoint boundary bounds that we obtained, they were coinciding with the spherical ones, which are always, or have so far always been obtained with this Bourgain interpolation streak. But however, these boundary edges here, this Bourgain streak is not enough, and we need to argue differently. So instead of doing this single scale analysis in which we just aim for a gain in the frequency and some overall possible J's with this epsilon greater than 0, we need to keep the scales together. And the way to do that is we use, or one way to do that at least, is that we use this embedding that we had for the variation norms in the photo spaces, and we just keep the sum. We just keep the fact that this is a BR1 base of space. And then we want to prove this kind of like multi-scale sum operator bound estimate. So note that how this relates with what we already had. We had this kind of single scale bounds, right? And this, when you plug it into the above framework, this only gives you a little L1 norm in the right, but we want to upgrade it to a little LQ norm. And of course, if we had the epsilon, then we could, but we just don't have that epsilon, right? So we want to upgrade it, and let's see how we can do that. So many interpolation theorems, they go to put the scales together. These days, we just use the analytic interpolation, for instance, of Stein, which of course uses BMO. But how is BMO? BMO is defined through the sharp Pfefferman-Stein maximal function. So instead of applying an interpolation theorem as a black box, what we do is to use the Pfefferman-Stein maximal function to adapt it to our problem exactly, see what estimates we can obtain, and then just try to prove what we want for our specific case. So remember, this is the definition of the sharp maximal function, which the sharp maximal function has a larger LQ bound than our original function. And we will use that with our multi-scale sum of taking the LR norm in time, and then we will take LQ norm on a space of that object. And that gives us to 3 different terms of, and here the gain is that we are subtracting the average, right? So here, this subtracting this average is gonna give us a gain. So then when we look at the Pfefferman-Stein sharp maximal function for this object, we can divide into 3 different types of terms. So, and it's better to understand this term when we fix, let's say, we fix like a scale, 2 to the j scale in frequency. What is the reciprocal scale? Is 2 to the minus j in space. Our operator is essentially constant at that scale. So then if we look at cubes that are smaller than the scale at which is constant, so here what we'll use is the cancellation, the usual trick, right? Already coming from Calderon-Zygmunt theory, in order to get a gain from the fact that we have like a smaller support and be able to sum overall possible scales that are below. Then what happens if we take very large cubes, let's say cubes which are of size greater than 1. So in that case, that is the case G3, and that is also going to be an easy term to handle. In this case, it's like an error term. It's like even much easier. So why is that? Because our operator was local. Remember that the time was localized between 1 and 2. It doesn't delocalize the input function. So so this term is like if it weren't there. So we only need to look at cubes of size 1, essentially, at most 1. So then the term that we are left with is we have this fixed frequency here, and we have cubes that are larger, but there's more than 1 of this configuration. And this is what we look at. This is the crucial term. And in that case, the cancellation is not going to play any role because we already got a gain from the small support for the other term. So we can just like forget about the difference with the average and just look at this term. And here, one of the gains that is going to come is from the fact that we have fewer terms and that we are taking an average. And let's see how to get that gain. So the first thing is that we first use a Fubini to kind of pull the sum out of the supremum, and therefore we can discretize our operator as a sum of other operators, which are maximal functions. So here we sum over all possible ends, and what we are taking into account is the difference between we are summing for all n, and n means the difference between the scale, the frequency scale of the function, and the size of the cube that we look at. So then we look at one of the single operators, and it's the same as if we just prove a favorable estimate in that difference of scales. That is if we prove a decaying estimate with the parameter n for some positive epsilon PQR. Okay, so let's look if that's possible. So this is our operator. Again, here we had already the single scale estimates, right? That the single scale estimates in this language that we have reformulated, they are estimates which are uniform in n. They don't have the gain as it was before, right? We are missing that gain in n to the in 2 to the minus j epsilon. Here it manifests as no gain in n. So how can we obtain a gain in n here? So the thing is that this is a maximal function. So maximal functions are most powerful or easier to obtain bounds when we are in L infinity. So, and this is what happens here. When we look at L infinity, there is a crucial gain. There is a crucial gain in n that therefore can be interpolated with the uniform estimates to yield the bounds that we want in the interior here of this blue region, and which is where our boundary edges are lying. So, and how can we do that? At L infinity, the benefit is coming from the fact that having taken the sharp maximal function creates an average, is localized, one can just do Helder, apply the fixed time estimates, and then one gets the gain. Once you are decompose everything and localize enough so that you are putting this L infinity situation for a maximal function, we have already won. So this is the basic idea for this endpoint estimate. So let me conclude with a nice corollary of our results, that which was one of the things that motivated the study of the LPLQ estimate, is that it yields a sparse bounds for spherical maximal functions, for variation of spherical averages via a generalization of Lacy's sparse domination in the context of variation norm operators. So with this, I want to finish. I think I went a few minutes over time, but I hope this was enough. This was okay. So thank you for everyone who has been watching until here, and I'm looking forward to your questions.